Hello, and welcome to Chemistry Corner. I'm your host, Mr. Sellers. So, if we're doing the e-learning day lesson today, that means that the COVID-19 has spread enough that we felt it was necessary to shut down schools temporarily. I just want to take a few seconds at the front here to make sure that you're aware of some safety tips to keep yourself healthy during this time. It's going to be pretty much the same things that we do every flu season. Wash your hands, cover your mouth when you sneeze, not with your hand, but with your elbow, things like that. If we have decided that the spread is serious enough to close down the schools, you should probably also avoid other crowded places. So going to the gym, going to the grocery store, big crowded movie theaters, things like this, it would be only if it's really, really necessary. Otherwise, slightly putting yourself at risk being in a large crowded place like that. I'm sure that you are already aware of these tips. I just want to remind everybody, make sure you're watching out for yourself, staying healthy. So our actual lesson today is going to be more of a review lesson. I want to go back and cover some of our basics again about the atom. And then we're going to really, really focus on balancing ionic compounds. This is something that we've already been quizzed on twice now. But I think that it's a good thing to keep hitting because it's the skill that we need to build on top of as we move through this trimester. First, let's quickly review the basics of the atom. Atoms are the building blocks of matter. Matter is anything that takes up physical space. So when we think about atoms, they're made up of these things called subatomic particles. We've got three subatomic particles: protons, neutrons, and electrons. And there are a lot of ways that I can portray an atom, different ways that I can draw it. These are obviously not to scale. Atoms are very small. They're also not proportionate. We've learned that the nucleus takes up a very small space, and the electron cloud is what takes up most of the area and the volume of the atom. So, atom basics. The nucleus. It's where the protons and the neutrons exist. It's where almost all of the mass of that atom exists. And it is positively charged. The protons are bringing the positive charge, and then the neutrons are neutrally charged. They have no charge. So overall, the nucleus is positive. Outside the nucleus, we have the electrons. And they don't move in perfect circles, like Bohr might have said. The electrons are actually moving in these things called orbitals. Sometimes we call them electron clouds. The electrons are negatively charged. That means that all of this area outside the nucleus is negatively charged. Protons and electrons attract each other. That's that positive and negative attraction there. And that's kind of our basics of the atom. We've got protons, neutrons, and electrons. They interact in certain ways. One way that I might portray an atom is with the Bohr model. I like to draw my Bohr models with the nuclear charge in the middle. All of these are oxygen, and oxygen has 8 electrons and 8 protons. So when I draw it this way, thank you, Lua, I've got my 8 protons in the nucleus here, and then I've broken up my electrons into 2 different energy levels for oxygen. Oxygen has electrons in the first energy level, but just 2, these ones. And then it has 6 electrons in the second energy level. Those are these ones in this second energy level. And remember that we call those valence electrons. The ones on the outermost shell are the valence electrons. What I'll be drawing most often today for this lesson are going to be Lewis dot drawings. Lewis dot drawings show the element symbol O for oxygen. And then they only show the valence electrons. So I didn't need to show these inner electrons when I was drawing my Lewis dot drawing over there. I only showed these 6 valence electrons. I don't need to distinguish between s and p orbitals. These are all in the same valence shell, so I can just draw 6 dots around my O for oxygen there. These are our basics of an atom and how it's put together. Alright, so we went over our basics of the atom again, but most of the time when we think about atoms, they're not individual atoms. Usually we have many atoms in one place, and these atoms are usually not alone either. They're usually bonded to some other atom, maybe even another element. So quickly, going over our different types of bonding again. We've talked about ionic and covalent bonding the most in class. We have talked about metallic bonding a little bit. I'm not going to cover that again in this video though. So, 3 examples that we've got here of different bonds that we might see form. We'll start with our salt example here, sodium chloride. Now sodium has 1 valence electron. All of the alkali metals only have 1 valence electron. Chlorine has 7 valence electrons, and all of the halogens will have 7 valence electrons. Sodium would really like to get rid of this electron. If it can lose this electron, it's going to end up with a full octet. It'll be very stable. Chlorine would like to gain 1 electron. If it gets that electron, it will also have a full octet, and it'll be very stable. They're able to have this relationship because chlorine is much more electronegative than sodium. So a quick refresher here as to why chlorine is more electronegative than sodium. I forgot to label these. This one's sodium, atomic number 11. This one's chlorine, atomic number 17. So why is chlorine more electronegative than sodium? They're in the same period. They're in the same row on the periodic table. That means that they're both having electrons in the 3rd energy level. That's their valence shell, is this 3rd energy level here. But the difference is, chlorine has a much more positive nucleus. It's got 6 more protons than sodium does. We can think of that like a stronger... Thank you, Lua. She just shook my hand. We can think of that like a stronger pull. So chlorine, my bad. Chlorine is more electronegative. It has more protons in the nucleus. It's able to attract those electrons much more easily. Chlorine is more electronegative than sodium. That means that it's stronger. It's able to attract electrons easier. Chlorine, its nucleus, it's got this positive charge in the nucleus. And this negative electron is attracted to that positive charge from the nucleus. It's more attracted to chlorine's nucleus than it is to sodium's nucleus. So this electron is going to end up being completely transferred. It'll go from our sodium atom over here to our chlorine atom. Now when that happens, both of these atoms have now become ionized. We made them into ions. Sodium lost an electron, and electrons are negative. If I lose an electron, that gives me positive charge. Chlorine gained an electron, electrons are negative. Chlorine now has a negative charge. This is the attractive force in an ionic bond. We've got that positive charge from the sodium and the negative charge from the chlorine. These are attracted to each other, just like a magnet. Salt, sodium chloride, is a polar molecule. We know that it's polar because it has poles, like a magnet. It has a positive end and a negative end. So an ionic bond, it's not an actual sharing of electrons, it is the transfer of electrons from a less electronegative element, a metal, to a more electronegative element, a non-metal. This gives them full charges, and those full charges attract those atoms together and hold them in place. They bond. Let's talk about a different type of bond. Let's talk about water. Water does not form ionic bonds. Water is going to form covalent bonds. Let's check out the Lewis dots. Oxygen, we did this one already, it's got 6 valence electrons. Hydrogen only has 1 valence electron. I've got 2 of them, H2, but each one only has 1 valence electron. Oxygen is going to try to fill the octet rule. It would like to have 8. Hydrogen fills something called the duet rule. It only needs 2. Remember, we can only fit 2 electrons in that first energy level. We're not going to see a complete transfer this time. Both oxygen and hydrogen are non-metals. That's how we know that this is going to be a covalent bond, 2 non-metals bonding together. Now, oxygen is more electronegative. Oxygen is stronger. It's able to attract those electrons more tightly. So what we're going to see happen here, oxygen is pulling on the electrons from hydrogen. At the same time, hydrogen is pulling back on the electrons from oxygen. We're going to end up maybe with something like this. The electrons are being shared between both atoms, here and here. But it's not an even sharing. The electrons are going to spend more time near the oxygen. It's difficult for me to show you, but remember that these electrons are in motion. They're moving. They might spend some of their time here really close to the hydrogen atom, but they're going to spend most of their time over here near the oxygen atom. That's because the oxygen is more electronegative. It's attracting those electrons much more strongly. So I'm going to draw these as regular bonds now. This is something that we don't do with ionic bonds because it's a different attractive force. These bonds, these lines, they represent 2 electrons being shared. 2 here and 2 here. Now, this is a covalent bond. But water has polar covalent bonds. Sometimes we can draw that with special arrows that look like this. This is not something that I've shown in class before. What these arrows are showing us is that these are polar bonds. It kind of looks like a plus sign on these ends. That's because these hydrogen atoms are partially positive. The electrons aren't spending as much time on these hydrogen atoms, and that makes them partially positive. It's not a full positive charge like sodium got up here, but it is a little bit. And then the arrowheads, they're showing the movement of the electrons. These electrons are spending most of their time here, closer to oxygen. That makes the oxygen partially negative. It's not a full negative charge like chlorine has, but it is partially negative. This separation of charge makes water a polar molecule. It does have a separation of charge. More positive here, more negative here. It's not as extreme as an ionic bond. It's a little bit in between. Remember that this is a spectrum. Okay, awesome. Let's get this last one out of the way here. Diatomic oxygen. This is the elemental form of oxygen. 2 atoms bonded together. Each have 6 valence electrons. They'd like to get to 8. They could make a single bond, sharing 2 electrons here, but now they're both at 7. That's not an octet. That's not enough. Oxygen, diatomic oxygen, is going to bond with these double bonds here. Each line represents 2 shared electrons, 4 total in a double bond. Now this oxygen has a full octet. This oxygen has a full octet. They're both very stable. I'm not going to draw arrows like this this time, because both of these oxygen atoms are equally as electronegative. They're identical. They should be. They're both oxygen. If they're identical in their electronegativity, neither one has an advantage over those electrons. The electrons are going to spend an equal amount of time near both atoms. I can't say that they exist exactly in the middle here. They do exist exactly in the middle at a given point in time, but they're always moving. These electrons are in constant motion. I'm just saying that they spend an equal amount of time near both oxygen atoms. So we can say this is an ionic bond. This is a polar covalent bond. And this is a nonpolar covalent bond. It does not have poles. It is symmetrical in its distribution of charge. Basic bonding, ionic versus covalent. Ionic is the transfer of electrons. Covalent is the sharing of electrons. They're not complete opposites. It's more of a spectrum. Now we're going to learn how do we balance ionic compounds. We're going to focus here on our ionic bonds for this next little bit. Okay, so balancing ions. We've already talked about where these ionic charges came from. It's from that transfer of electrons. So something that I haven't mentioned much in class, but these charges don't actually exist until those electrons have been transferred. So I usually will draw them this way with the charges already existing, but those charges come after the electrons have been transferred. Regardless, when we are balancing these ions, I'm trying to get the charges to cancel out. Positive charges and negative charges attract each other. They naturally would like to cancel out to 0. So when we're doing it on the board or on a test or a quiz, we're going to do the same thing. We're going to balance out to 0. In some cases, like our sodium chloride example, it's already done for us. Sodium with a positive 1, chlorine with a negative 1. These charges already cancel each other out. I can go ahead and just write NaCl. 1 sodium, 1 chlorine. That's enough. My charge cancels out. With something like sodium and oxygen, though, 1 sodium will not be enough. Oxygen needs 2 electrons to complete its octet, but sodium is only willing to give up 1 of its electrons to get to its octet. Remember what I said earlier, though. Atoms don't generally move around individually. If I've got 1 atom of sodium, chances are I've got thousands of atoms of sodium. So it's okay for me to bond them in different ratios. Maybe instead of 1 sodium, I've got 2 sodiums. If I've got 2 sodiums, each one can donate an electron to oxygen. Oxygen can get its 2, and they'll both be happy. They're all happy. Na2O, sodium oxide. This is a stable, balanced ionic compound because all the charge cancels out. Positive 2 from the sodium, negative 2 from the oxygen cancels out to 0. Same argument for this last one here. Sodium with a +1, phosphorus with a -3. 1 sodium is not enough. I'm going to need 3 sodiums this time. But if I've got 3 sodiums, it'll cancel out with this -3. Sodium phosphide Na3P. Sodium phosphide. Cancels out to 0. I'm going to show you a shortcut for this called the crisscross method. Many of you are already aware of the crisscross method. I'm going to lay it out explicitly here. Alright, so the crisscross method. When we have charges that don't cancel out, that means that we're going to need to add subscripts to our formula in order to make those charges cancel out. What we can do is we make sort of like a little crisscross here. The charge from one atom will become like the subscript for the other atom. And again, this charge will become the subscript on the other atom. So if I'm crisscrossing these ones, K2O, potassium oxide. If I've got 2 potassiums, that's +2. 1 oxygen, that's -2. They cancel out. Crisscrossing here, Al2O3. 2 aluminums, that's going to be a +6. 3 oxygens, that's going to be a -6. They cancel out again. Crisscrossing on this side. Al1, I don't need to write that one. Cl3, I will write this one. 1 aluminum, that's +3. 3 chlorines, that's -3. Cancels. Crisscrossing here, SnCl4. Crisscross method will work 90% of the time. Let's quickly look at times it won't work. So like most things in chemistry, the crisscross method does have exceptions. There are times that it's not going to work. If your charges already cancel each other out, you don't need to do the crisscross method. If I tried to do that, I would end up with Mg2O2. But this is not magnesium oxide. Magnesium oxide is just going to be MgO. I don't need to do that crisscross. These charges already cancel. Similar argument over here. I don't need to say Al3P3. I can just say ALP, aluminum phosphide. One of the last cases when it won't work, if we've got a +4 charge and a -2 charge. These are both even numbered charges, so crisscross is not going to work this time either. Instead, I'm going to say that this is SnO2, tin-4 oxide. Tin-4 oxide. It works out this way because 2 oxygens, each at a -2 charge, will give me -4. 1 tin-4, will give me a +4. That -4 and that +4 will cancel out. I don't need to do the crisscross. I can't do the crisscross for these exceptions. Alright, if you've made it this far in the video, I'd like to applaud you for making it all the way to the end. The last thing I'd like to talk about are the polyatomic ions and how we'll balance those. The polyatomic ions are ions, they're charged particles, but they've got multiple atoms to it. They're polyatomic. We're going to treat these as though they were one particle. So even though it might have 2 atoms or 5 atoms or something like that, we're still going to treat it like it's just one particle that's moving around together. So how would we balance that? We can still use the crisscross method a lot of the time. For this first one here, magnesium with a +2 charge. This is hydroxide with a -1 charge. I can do the crisscross method. I can take this 1 and make it the subscript for my magnesium. Magnesium. I don't need to put this subscript of a 1. It's understood that I only have 1. And then this charge of a 2 will become the subscript for my hydroxide. Just remember to put it in parentheses. We're treating it like it's one particle. If I'm treating it like it's one thing, I need to make sure I've got 2 of both elements. So magnesium hydroxide is going to be MgOH in parentheses 2. Let's crisscross a few more of these. Sodium and phosphate over here. I'll use this 3 as the subscript for the sodium, Na3, and then a 1 for the subscript for the phosphorus. The thing is though, like I said, I don't really have to put a 1 here. These parentheses and this 1, they're not really adding anything to my formula here. I don't really need those. I can take it out. I'll redraw this here. Sodium phosphate is just going to be Na3, PO4. I still crisscross though. Crisscrossing this one, I've got ammonium and carbonate. 2 is going to be the subscript on the ammonium. This time I will need parentheses. This subscript, this 2, is not part of ammonium. It's not part of this polyatomic. It's something extra. So I put it outside in parentheses. Outside the parentheses. And then this charge of a 1 will become the subscript for the carbonate. CO3. And again, this time I don't need the parentheses. I don't need to put a 1. It's understood that I only have 1 carbonate. There are still exceptions where I won't be able to use crisscross, like calcium and sulfate here. Positive 2 and negative 2, these charges already cancel out. I can just go ahead and bond these together as they are. Calcium, sulfate, calcium sulfate. Okay, awesome. So at this point, we have covered the basics of the atom again. We talked about the basics of bonding again. I showed you how to balance ionic compounds. I showed you the crisscross method, and I showed you how to balance with polyatomic ions. At this point, you are definitely ready to do the very small assignment that I've made for you. If you are feeling really confident and maybe you're just home bored, you can go ahead and do the entire table and chart that I've made. But for this first day, I'm really just expecting you to balance the ionic compounds. And I've labeled that very clearly in that document. Again, thank you for making it all the way through the whole video. I'll get Lua in the shot here, and again, as a little reward. Come here, Lua. Stand up, stand up. Come say hi. Come here, come here. Come here. So your only homework is to work on that document that I posted on Classroom, and stay healthy too. That's also my homework for you. All right. Thank you for making it to the end. Have a good one.